In statistics, a histogram is a graphical representation of a variable in the form of bars, where the area of each bar is proportional to the frequency of the represented values. They are used to obtain a general first view, or panorama, of the distribution of the population, or of the sample, in this case of the simulated numbers, with respect to a characteristic, quantitative and continuous, the magnitude of the risk. In this way, it offers an integral vision allowing to observe a preference, or trend, on the part of the simulated data, because it is located towards a certain region of values within the spectrum of possible values, whether infinite or not, that the evaluated characteristic can acquire. Thus, we can demonstrate behaviors, observe the degree of homogeneity, agreement or conciseness between the values of all the parts that make up the group of simulated data, or, in contrast, be able to observe the degree of variability, and therefore, the dispersion of all the values that the parts take. The vertical axis represents the frequencies, that is, the amount of simulated data, as the case may be, that is located in a certain value or sub-range of values of the characteristic measured here, which is the monetary magnitude of the risk. Obviously, when this spectrum of values is infinite or very large, it is reduced to only a part that shows the trend or behavior of the population. At other times, this spectrum is extended to show the distance or location of the simulated data from a value of interest. Histograms are used to relate continuous quantitative variables, which is the case of risks calculated by the product of their frequencies and their severities. By the way, for DT simulator to collect data from any cell, it must have been previously declared as an output variable. I had done this from the beginning, when I built the model, positioned myself on cell B18 and declared it as an output variable with the output data icon. By clicking on the Show Outputs button, you will be able to observe the previous existence of such a cell as an output variable. Position your cursor over cell B18 that contains the only output variable of this model, which is the loss, according to what has been previously specified in the selection of risk categories and administrative units. Also, make sure that the Monte Carlo simulation has been run with the number of iterations you have previously chosen. In my case, I have previously used 50,000 iterations for this process, which took me about 16 minutes to execute. I have simulated for all risk categories for all administrative units, which would be the maximum level of aggregation. With the calculation that we have made of the operational risk, we are now ready to properly estimate the valuation of the reserve capital for operational risk. As we have seen, the Basel II Banking Supervision Committee has proposed a methodology to evaluate such capital allocation for operational risk with this methodology called the aggregate loss distribution approach. We have assumed that the loss event is the composition of two events, one called frequency and the other severity, both considered convolutionally. For the calculation of regulatory capital, the concept of value at risk is applied to the context of operational risk, adopting the OPVAR nomenclature, operational value at risk. The OPVAR represents a percentile of the loss distribution and reflects large losses caused by operational risk. While the VAR is generally defined as the capital sufficient to cover losses of a portfolio over a fixed period of time, conventionally determined here in 1 year. Risk exposure is calculated as a percentile of the loss distribution function. Basel II requires the percentile to be 99.9%, but it can easily be changed to any other percentage. It is enough to modify such data in cell B8. We are going to use the 99.0 percentile for our example. In this way, observe in the simulation results table in column E how the operational value at risk is composed by its two components, the expected loss plus the unexpected loss at a certain level of confidence, in this case, 99%. The sum of both elements constitutes the operational value at risk. The expected loss is the average of all the losses. The 99% operational value at risk is calculated using the Excel percentile function on the simulation data generated. The unexpected loss at the specified confidence level is the difference between the operational value at risk and the expected loss. You must be careful that, once you have changed the risk category to be assessed or the respective administrative units, the Monte Carlo simulation must be run again so that the data is updated respectively. The table to the right shows the main statistics. With 50,000 simulated iterations, the lowest possible total risk value is nearly $63,000. The maximum value approximates $139,000, causing a range of variability greater than $76,000. The average value is around $98,000 and the median or 50th percentile approximates the same value, which tells us about a lot of symmetry in the distribution, a fact that is confirmed by the fact that the asymmetry index approaches 0. The 20th percentile is approximately $90,000 and the 99th percentile, with which we calculate the operational VAR, is somewhat over $121,000. You can set lower and upper limits for percentiles and target values. For example, at this time the two target percentiles have been set at 20 and 99. The two target values have been arbitrarily set at $0 and $1,000. These four statistics can be modified with the parameters icon on the DT simulator ribbon. We go to parameters and modify the following parameters. We set the first percentile value at 50, the second percentile at 99. On the other hand, looking at cell F3 of expected loss, we write the value entered there as target value 1, in my case it would be $98,068. I set the target value 2 at the operational risk value entered in cell F5 for $121,211 in my case. Once these four values have been entered, I proceed to confirm, deciding not to simulate again, since setting these parameters only modifies graphing parameters and does not change the simulated data at all. This saves me all the unnecessary simulation time. Immediately, I proceed to click on the histogram icon, previously making sure that the cursor is still on the output cell B18. The graph will now look like this. With these two blue delimiters respectively above the expected mean and the 99th percentile, the three segments specified in the table in column E are marked. We can then calculate the probabilistic contingency that is actually the unexpected loss, in this case for $23,143, which, as I have indicated, is the unexpected difference between the operational value at risk and the expected losses. Notice that DT Simulator also calculates the probability of each of the segments. Being such a symmetric distribution, the mean expected loss is practically on the cusp or mode and equals the median at $98,000. Therefore, there is a 50% probability that losses will occur up to this expected level. By definition, there is a 49% probability that there will be losses for an additional $23,000, reaching an operational value at risk at 99% confidence for a total of $121,000.